Minutes. I request all the participants to wait a while.
నాకు క్లాస్
Thank you.
ఉంది అట్టే వస్తున్నాను.
అక్క ఒక్కసారి నీ సిస్టమ్ చూడవా ఒకసారి అప్డేట్ అయిందా ఇందాక అప్డేట్స్కి వెళ్ళిపోయింది డిఫాల్ట్గా అది ఇందాక అన్నాను కదా అప్డేట్స్కి వెళ్ళింది అక్క అనేసి ఓకే ఓకే నో ఇష్యూ లేండి ఇంకా టైం అవ్వలేదు ఇంకా స్టార్ట్ అవ్వలేదులేండి Good morning, sir.
Yeah, good morning, sir.
Yeah, and sir, we can start, sir.
Yeah.
Yeah, okay, sir. Can you share your screen once, sir?
Yeah. Thank you.
Sir, so today we'll be discussing about the classification.
Yeah, correct.
Yeah,
Classification, different classification methods.
yeah, okay, sir. Yes, sir. We can see your screen, sir. Yeah,
Yeah,
dear
thank you.
participants, once again, welcome to the third day of our FDP program. So once again, the session will be handled by Ailay Garu from NIT Warangal. He will be discussing about the classification, different type of classification techniques and algorithms, sir.
Okay.
So over to you, sir.
Yeah,
Thank you, sir.
yeah. Thank you, sir. Thank you, sir. Dear participants, good morning to all of you, and welcome to the session on classification techniques, different classification techniques. So yesterday we covered regression analysis with hands-on, right? So today, yeah, we discussed these things, right? Yesterday, what is supervised learning? So types of supervised learning, like regression, classification, right? So then, what are the regression techniques? Linear regression. Then we also discussed the logistic regression and what is the difference between why the name logistic regression, even though it is a classification mechanism, right? So today we'll continue with this K&N classifier, support vectors, neighbors, and decision trees, if possible, random forest, right? Okay, right. Now coming to the K&N classifier. So this K&N classifier is basically assumes is based on nearest neighbor mechanism. So nearest neighbor, actually, what is mean by a nearest neighbor? So how we can say a particular object is very nearest to to some object. Okay, how we can say that they are uh, two objects are neighbors. Okay, so we need to have some similarity mechanism. So that here generally the similarity mechanisms used are some Euclidean distance based or Manhattan distance based or some correlation techniques we'll use. Okay, so here, to measure the nearest means whether a object is neighbor or not, we'll need to use some distance measures. Okay, similarity measures. Okay, if that particular object is very close to, right, neighbor means they are very closer to our house or they are closer to our cabin, right? My neighbor in my means is that my room, right? Means he's the neighbor means he's very close to my room, right? So like that here also we need to use some distance measures. We need to consider some distance measures. So here KNN algorithm assumes a similarity between a new case and the available cases and put the new case into the category that is most similar to the available categories. Let us assume we have a set of groups. The KNN algorithm at the time of suppose to which class that particular object belongs to, right? So the new data point or whatever it may be. So compared with all those neighbors in that means all those objects in that space, and the based on the means which particular objects are very close, and to that particular objects class. Now we'll categorize the test data into that particular. Right. So how this algorithm will work now, you'll see. Here an algorithm stores all the available data and classifies a new data point based on the similarity. This means when a new data point appears, then it can be easily classified into well-suited category by using KNN algorithm. Here, an important thing with KNN is that it is a lazy learner algorithm, because like logistic regression or naive Bayes or these decision trees in KNN, there is simply the training phase is not that much actually. So the training data actually will be stored in a table, and if a new occurrence occurs, this new data point will be compared with all the table records. Okay, so here see, it is also called a lazy learner algorithm because it does not learn from the training set immediately. Instead, stores the data set in a table, and at the time of classification, it performs an action on the data set. Kernel algorithm at the training phase just stores the data set, and when it gets new data, then it classifies the data into a category that is much similar to the new data. Okay, we'll see how this algorithm will work with an example. Then, if you have any questions, we'll discuss. Let us assume here we have a set of data points. Those data points are categorized into category A and B. And if we have a new data point X, so this data point will lie in which of these categories, right? So we have already categorized the given data into some categories, right? Category A and B. Now, if a new data point occurs, so to which category it belongs, right? So to solve this type of problem, we'll use kernel algorithm. Suppose if you see in a two-dimensional space, we plotted a few objects here, like some cats and dogs are there. So based on their features, you can see here, based on their weight and height, they are plotted on the two-dimensional space. See here, not only two-dimensional but n-dimensional we can use. But here for simple understanding, just I taken this two-dimensional space and consider only two features: it is weight and height of the objects. Okay, so suppose generally, the cats will have less weight and less height compared to the dogs. So dog will have more weight and height is also little bit higher compared to cats, right? Now these objects, cats and dogs are classified, means plotted, not classified as of now, right? So these are plotted in the two-dimensional space. Now we can easily segregate them into two different classes, because the dogs will have higher weight and higher height compared to these cats, so that these objects will fall under one category, and the cat objects will fall under another category. Let us assume this is class cat and a class dog, the left side diagram. Now coming to the right side diagram, if a new data point, so new data point is represented using this orange bubble, orange circle, filled orange circle. Now, if this new data point comes, so in which category it will fall, whether it is a cat or it is a dog, right? So now we need to predict. We need to predict whether it is a class cat, whether it is a cat or it is a dog. So so yeah, in this case, now we'll see how the KNN algorithm will means predict to whether it may belongs to cat, whether it may be cat or dog. Right. Now this new data point, you can see here the weight is 85 approximately and the height is 2 feet. Right. Okay. Now, how does the KNN will work? We'll see step by step. Right. Okay. The first step in KNN algorithm is we need to choose the K value. So how many, what is the K value? So how many, suppose let us assume in our department also, I need to identify a person, whether he belongs to CSE or whether he belongs to like ECE or Triple E, like that. So how I can say, suppose based on my, what is this called, my sitting place, my cabin. So if I compare my cabin, means my cabin position with who are the neighbors of my cabin? CSE people only, right? If a new person comes, he's sitting in one of the cabin. So some external person, if he comes, he wants to say whether he belongs to CSE or ECE or Triple E. So if I sit in CSE cabin, then I may belong to CSE, right? So like that, to identify a particular, to predict a particular object to which class he belongs, so we need to compare with his neighbors. Suppose colony also, let us assume whether you belongs to you belongs to Hyderabad or you belongs to Hyderabad, or so based on what So if you are in the locality, what the information about your neighbors is required, right? Your neighbors also in your place like Nizampet, right? So you are in the Nizampet, right? If your house is in some other place, so if I have the information about your neighbors, like your neighbors, then I can predict easily that you belongs to Kukatpalli or you belongs to Madhapur, right? So here also for that, we need to first identify the neighbors. So neighbors, how I need to identify based on the distance, right? So here we will use Euclidean distance, or we can also use some Manhattan distance, or we can also use some other some lot of distance measures are there. So we can use any one of them to measure the neighborhood, means to find out the neighborhood, right? So first select the k neighbors. The second step is calculate the Euclidean distance between the test data point and all the training sample points. All the training sample points. Suppose let's say in your the database 10 samples are there, right? One fellow is one fellow is in Kukatpalli, one fellow is in Nizampet, and other like that. Some data is there, right? Now my information I will provide right now with my so I need to identify whether to which particular category he belongs, right? So in that case I need to find out the distance from this particular test data point to the all the training sample points. So from that we need to take the k nearest neighbors. So k nearest neighbors. Okay. So as per the calculated Euclidean distance. So among these k neighbors, count the number of data points in each category. Assign the new data points to the category for which the number of neighbor is maximum. So voting mechanism we need to use here. So but which category the votes are maximum. Okay. So we'll see with the real time example. See here now this suppose if you take this data point now these are all training samples. So 4 plus 2 6 cats are there and 6 dogs are there. So first I need to calculate the distance to all these training sample points from this test data point from this arrange circle. So I need to find out the distance to the these 12 samples. Okay, so after that which are having minimum distance, which are having minimum distance and by specifying using the k value, right? So now among these 12, if I choose k equal to 3, I need to consider 3 neighbors. So who are these 3 neighbors? Who are these 3 neighbors? Right? So if k equal to 3, you can see for this data point, these 3 neighbors, in these 3 neighbors, 2 are cats and 1 is dog. 2 are cats and 1 is dog, right? So now based on this information, now I can assign this particular object to the class cat. Okay, if k equal to 3, the new data point, we can say that this belongs to the cat class. Now, if I increase the k value, let us assume k is chosen as 7. K is chosen as 7. So just see here, if I choose k as 7, among the 7, see that's our second circle, outer circle including the inner circle, because among the 7 objects, now the nearest 7 objects, right? 3 are cats and 4 are dogs. Yeah, 3 are cats and 4 are dogs. Now tell me to which class this particular object belongs. So to the class dog. Okay, so like this, you can see here if k equal to 3, we can say that it is belongs to cat class. But if k equal to 7, we can say that it is belongs to dog class. But which one is correct? Okay, so while doing experimentation, so the k value is very, very important in k nearest neighbor algorithm. Okay, so now come back to this this algorithm here. What we need to choose first, k value. Then we need to calculate the distance from this point to all the training samples. So from that, the third step, what we need to choose? We need to choose the nearest k neighbors. So among those k neighbors, we need to do the voting process. count the number of data points in each category. So voting of different classes. So two cats, one dog. If k equal to 3, right? If k equal to 7, what is the majority here? If k equal to 7, the majority is dogs, right? So like that, we need to do. Now, the last step is assign these new data points to the category for which the votes are maximum. The number of neighbor is maximum, right? So like this algorithm will work. Okay. But choosing K is very, very important in K-NN classifier, right? This because we have to do experimentally. So where we are getting good results. So based on that, we need to finalize K value. So less K values results generally, misclassification will be there. But if high K values maybe sometimes leads to means you may get means the accuracy may it may go down sometimes. Okay, so choosing that K is very, very important. Default generally the K value will be chosen 5 for some data set, 5 actually. Right, now coming to support vector machine. So at the end, we'll see small demo. I'll take 10 minutes for all these algorithms because yesterday I explained the pre-processing step, right? Just I'll take 10 to 15 minutes at the end for demonstrating how these algorithms will work on different assets. So how to simulate, how to experiment using how to train these models for different data sets and how to predict the accuracy of the system. Support vector machine algorithm. So here with support vector machine algorithm, this is works based on a decision boundary. So we need to find out a decision boundary that segregate the n-dimensional space, the given space, into different categories. Right? We need to draw a decision boundary so that the left side is one class, the right side is another class, right? The top one is other class, the below one is. So like that, we need to draw some decision boundaries. Sorry, decision boundary, so that we can segregate into different classes. Multi-classes or binary class. In multi-class, we may have more than two classes. In binary class, we have only two classes, right? Yes, no. Right? Yesterday we saw this binary class classification, right? Whether survived or not in Titanic that incident, right? Survived or not. Likewise, suppose if I want to segregate animals into different categories: dog, cat, elephant, tiger, lion. So that is multi-class classification, right? So if we segregate this given training data into different classes, then we can easily put the new data point in the correct category in the future. The prediction will become very easy. So the best decision boundary is called the hyperplane. So this decision boundary generally will be called the hyperplane in support vector machines. How this hyperplane will be chosen and different terminology related to this one we now will discuss. The support vector machine chooses the extreme points, or these are called support vectors. Extreme points are support vectors that help in creating the hyperplane. Now, what are the support vectors? Okay, so the extreme cases are called support vectors, and hence the algorithm. So the name is the extreme cases or extreme data points in the training set are called support vectors. So the name is called, that's why the name of this algorithm is called support vector machine algorithm. See here, you can see we have a set of data points. So among these data points, you can see here the support vectors. 3 are chosen as support vectors. Just observe here among all these, because these are, suppose if you compare with this left side objects, the right side objects, here in left side, all the objects are very closer to each other, right? And right side also, these objects are very closer to each other, right? So there is a lot of similarity in the means individually, right? They are very closer in the left side objects as well as right side objects. But if you observe The distance from this left side objects to the right side objects is very high, right? So based on the situation, suppose the extreme end of these particular objects, right? So these are chosen as support vectors, and the beginning of the second class or second type of objects will be chosen as the other right side of the support vector for the hyperplane. So these are chosen as hyperplane. Sorry, these are chosen as these data points are chosen as support vectors, and based on the support vectors, now we need to draw the hyperplane. Okay, so this particular line whatever here taken is called the hyperplane. Now we'll see what are the different conditions how to select a right hyperplane and how does the SPM will run. Okay, so this hyperplane can be generally a simple line or a different kind of means we call it a addition, a different kind of boundary also means an square or a circle or an ellipse. Okay, it may be straight line or some other method means it may be a circle or it may be a ellipse or it may be a curve. Okay, whatever based on the objects given, the hyperplane shape will be depends. Okay, but here you can see simple. There are two different types of objects. Now we drawn here three different hyperplanes. These are called actually uh, uh, linear, linear line or linear hyperplane. See, so here A, B, C, there are three hyperplanes, but which one is the correct? Which one is the correct? So here, based on A, B, C, if you select A, so it is segregating the second class into again two classes, the circles into two different classes, but that is not correct. So misclassification is there, right? So 5 circles are on one side to the A, and 3 circles are it is segregating into the class stars, right? Now if you consider C, 2 circles are segregating into stars class, and 5 classes or 6 objects are segregating into another class. But if you observe B is segregating the 2 classes perfectly, right? So that's why so you need to choose the hyperplane which segregates the classes better, right? So in this scenario you need to choose B. Okay. Now coming to the second scenario, here like B, A and C also there, right? There are three hyperplanes. Let us use A, C, B, but among that, which one is the good? Which one is the best hyperplane? So again, here we need to consider the maximum means the hyperplane which is having maximum width, or that is generally we can call it as the distance between the hyperplane and the extreme point, the support vector is maximum. Okay, so the maximum, so we need to choose the hyperplane that maximizes this distance. So maximizing the distance between the nearest data point from either class and hyperplane will help us to decide the right hyperplane. So among this, suppose if you see C is having, suppose from the stars B is very close, right? From stars A is having maximum distance, but from circles A is having low distance. But if you see C is moderate, right? From stars it is a little bit higher distance, as well as from stars also, sorry, from circle also it is having a good distance, right? So that's why we need to choose C as the correct hyperplane. See here in this diagram, you can see that the margin for the hyperplane C is high compared to both A and B. So hence we name the right hyperplane as C. Okay, so this will maximize. So one more important thing is that if it is a little bit distance, so we can perfectly segregate, right? So it is very robustness, right? Another lighting reason for selecting the right hyperplane with higher margin is robustness. If we select a hyperplane having lower margin, there is a chance of misclassification. Sometimes a new object comes, so where to place? Suppose it is very close to this thing. This if you select B, if it is very close to this, right? Let us assume B means it is on the B or like that. So in that situations, or if an object means if it is, let us assume the star is right side to B. The star is right side to means small deviation. Just it is just on B or just outside B. So in this scenario, what will happen? Actually, this is very closer to stars, but this B will classify that one as star. Sorry, circle, right? Suppose just assume here, you can see. Assume, suppose here, if we choose B, actually this is a star, right? But if we choose B as the hyperplane, this particular star will belongs to what? Circle class, correct? Correct or not? Because even though it is very close to, the stars, but it is misclassified as a circle, right? So that's why there should be maximum margin between these two classes to the hyperplane, right? Right. Now, the next category is again here BA. Two hyperplanes are there, but which one is best again? So the A is best, even though B is having maximum hyperplane in this case, even though B is having maximum hyperplane, whatever we saw in scenario 2, but here in this case, B leads to misclassification, right? Even though this is star, it is classifying as circle, right? So the SVM, so the hyperplane, even though it has to maintain maximum hyperplane, but the classification accuracy should be high. Classification accuracy should be at most important. Okay, so in this situation, so we need to choose A as the correct hyperplane. So accuracy is important, then maximizing the margin. Okay, so in this scenario, we need to choose A as the correct hyperplane. Now, suppose if this is the situation again. So how to classify? So here the star is called actually it is an outlier. Okay, these kind of things will be there sometimes. Okay, so anyway, we can't we are outliers to deal with this thing. Some pre-processing techniques we need to use, right? So some pre-processing techniques we need to use to increase the model accuracy, right? But outliers are always there in the data sets, right? So anyway, we can classify, but this is the hyperplane, right? Yeah. So up to now is a simple linear. What is that called? Linear hyperplane. But what I said, the hyperplane may be a circle. You can see in the third diagram. Maybe a circle or ellipse or different shape, some other different shape like some star, right? Or some other shapes. Right. So now find the hyperplane to segregate the classes. So the this is the example. The left side diagram is the example. That is the given objects are plotted in the two-dimensional space. The given objects are plotted in the two-dimensional space. Now, how to segregate using a linear hyperplane? Is it possible? Is it possible? No, right?
For second case, it is possible, no, sir?
No. Actually, second case is possible, but the first case is projected into a high dimensional space so that the diagram is looking like this. See
Oh,
here,
okay.
in the first case, there are only two means axis, X and Y. But in the second case, what happened? This particular objects are projected into three-dimensional space. These particular objects are projected into three-dimensional space. Now we can draw a linear line, right?
Okay.
Okay. So projection. So as it is the linear hyperplane. It is not possible, right? So in this scenario, the SVM kernels comes into picture. SVM kernels comes into picture. Okay. So SVM kernel, you can see here in the scenario above, we cannot have linear hyperplane between the two classes. So SVM classify, how SVM classify? So till now we have only looked at the linear hyperplane, right? So SVM can solve this problem by introducing an additional feature. Here we will add a new feature, that is Z. So Z is taken, and where Z value is equal to x square plus y square. So we'll have x coordinate value and y coordinate value here, right? For the left side image, left side coordinates, right? So these using this x and y coordinates, we'll find out a new coordinate, that is z. Now using z and x, we'll project these particular objects into the three-dimensional space. Okay, now we can draw a means we can create a hyperplane here, right? Right. So this projecting lower dimensional space to the higher dimensional space is called, actually, this can be done using SVM kernels, right? So we have different types of SVM kernels. So I'll explain you at the time of demonstration, right? So we have different types of kernel functions, actually. A sigmoid kernel and a Gaussian kernel and what is that radial bias function, RBF kernels. Other kernels will be there. So based on the application, actually we need to use those kernels. Okay, right. This is a simple example. Now coming to naive-Bayes classifier. Any questions, please? Completed two algorithms. Need to finish two more. If you have any questions, please ask. Actually, I'm not covering the mathematical part because nowadays, as everything. Suppose if you want to use this algorithm, simply you have ready-made packages are available. You can take them and you can fine-tune them, right? So that's why I'm not covering the mathematical proofs or whatever there in the whatever there in the literature. Okay. Right.
Sir,
Now coming to, yeah.
so this SVM kernel is basically a technique to project data from one space to
Lower
other.
dimension to higher dimension, where this linear hyperplane is not possible.
Okay.
In that situation, we need to use this SVM kernel functions. So that will project. So wherever being segregating is not possible, we can use these things. So we have linear kernels, polynomial kernels, sigmoid kernel, different types of kernel. Based on the application, you can use them.
Okay, and why are we interested only in a linear hyperplane?
Yeah, because for simple understanding.
Okay, because it's simple. Okay.
A simple understanding, because it requires a lot of complex mathematical things involved. That's why yesterday also I explained linear regression, not covered that multiple linear regression. Anyway, that is theory part we know, but for easy understanding, I explained. If you want, you can explore.
Okay. Okay, sir.
Now, coming to naive-Bayes, this algorithm is based on Bayes theorem. In probability theory, I think in second year BTech or somewhere, I think I studied this probability theory. right? Probability and statistics, I think. Okay. So this particular classifier is based on Bayes theorem for solving the classification problem. So mainly it will be used for high dimensional data sets. Okay, like text classification, example. Right. So it is called a probabilistic classifier, which means it predicts on the basis of the probability of an object, probability of occurrence versus probability of not occur. Right. So that's why this is called a probabilistic classifier. I'll maximize this. Yeah. So why it is called naive Bayes? So the naive Bayes algorithm is comprised of two terms, right? Naive and Bayes. So naive is basically, here it is called because it assumes that the occurrence of certain feature is independent of the occurrence of the other features. So there is less correlation between the dependent, less correlation between the independent parameters, right? So if the correlation is very high, means they are very similar. So the contribution of those two those two features leads to redundancy. So redundancy leads to obviously reduction of the accuracy, right? So this algorithm will be used if there is less correlation, because means they are independent of each other. So again, it is called Bayes because it depends on the principle of Bayes theorem. This is the Bayes theorem principle. Posterior probability of occurrence of A, if B is true, right? That depends on the probability of B if A is true, and probability of A by probability of B. This I will explain with an example, simple example, and the same example will see also for decision trees. Just a minute. Chodi is calling.
Hello.
Hello. This morning, sir, we are calling from HDFC Bank regarding service number.
మా ఇంట్రెస్ట్ లేదండి.
Sorry, very perfect interruption. Right. So we'll see how naive Bayes classifier will work. So here a small data set which is available taken, and see the data set consists of 14 records, 0 to 13, and here it is based on outlook, based on outlook whether play tennis or whatever, cricket or some play is possible or not. Okay. So here we have the past data available with us. So we need to give this to the classifier. So if a similar situation occurs, we need to predict whether play is possible or not, right? Suppose if rainy, here in this situation, in the first situation, play was there, but some other rainy here also play is there. But third occurrence of rainy here you can see this is eighth instance. So play was not there. So fourth instance, that is 11th instance, 11th record, you can see if there is a rainy, there is no play. So in rainy situation, there is you can say that out of 4 situations, 2 days, in 2 instances play was there, and in 2 instances there was no play. Right. So likewise, if if the weather is sunny, so there are sunny instances you can see out of 14, 1, 2, 3, 4, 5. Out of 5 instances, again you can see sunny. First instance it is play was there, and second instance it was not there, and third instance it is there, and fourth instance there was no play, fifth instance it is there. So around 3 out of 5 play was there, and 2 instance there was no play. So like that, if the weather is overcast, so you can see there are again instances 1, 2, 3, 4, 5 instances are there. Again, there was some play was there, and there was no play for some times if the weather is overcast. So this is the data available. Now we'll see how this data we can give to the naive Bayes classifier, and how the naive Bayes classifier will work to check whether here to check for the training, and at the time of predicting, if you see if the weather is sunny, then the player should play or not. So our classifier should answer this, right? So now how it will work, we'll see now. So the solution for this is here it will works in 3 steps. First, we need to convert the data set, given data set, into frequency tables. So frequency means number of occurrences of each event, right? And the second one is generate the likelihood table by finding the probabilities of given features. Okay, probability of play was possible, and what is the likelihood, right? So probability of play was not possible, like that. Now lastly, use the Bayes theorem to calculate the posterior probability, right? Whether play was there or not, use Bayes theorem to predict that. So the first thing is frequency table for the given weather conditions. So if the weather is overcast, play was there for 5 times out of 5 situations. So there are totally, totally 13 records are there, correct? 14 records. 14 records are there. In that, the weather is overcast. Every time play was there. Every time play was there. You can see here. Overcast S, second record, third record, as well as 7th record, 12th and 13th. If the weather is overcast, then play was there every time. So play was possible. Play was there, right? So overcast, play was there for 5 times, and 0, no cases, right? If there is a rainy, so we already verified, right? So from the data set, we can see that 2 times play was there, and 2 times there was no play when the weather is rainy. And in sunny situation, 3 times play was there, and 2 times play was not there. Actually, this is a typing mistake. You can see for a total play was there for 10 days out of 14 days. Out of 14 days. 14 situations. And 4 times there was no play. 2 plus 2, 4. Actually, this is typing mistake. So it should be 4. So 10 plus 4, 14, right? So this is the frequency table, occurrence of how many times play was there and how many times play was not there, different situations, right? Now likelihood table of the weather condition. So this is a probability. You can see here if there is overcast, every time play was there. 5 situations. So that is this table. Now, among all these situations, there was no play for 4 days out of 14 days. So the probability of no play is 0.29, and the for S is it is 0.71, right? So this is 10 by 14, this is 71, and for overcast you can see the likelihood value, that is 5 by 14. Out of 14 days there was the weather is overcast. The weather is overcast, right? So out of 14, 5 by 14, this is 0.35, and rainy 4 days, right? 4 out of 14, that is 29, and sunny, this is 5, right? So 5 by 14, out of 14 days, 5 days sunny. So this is a likelihood table. We'll apply the base theorem to find out if the day was sunny, right? If the day was sunny, play was possible or not. Sorry, play is possible or not. Okay, the day is sunny, we need to predict whether can play or not. So we need to find out whether yes or no. So we'll try to find out the probability of yes if the day is sunny, and probability of no if the day is sunny, right? So here P of probability of S, correct? If sunny is true, this is a posterior probability, right? Whether play was, what is the probability of S if the sunny, the day is sunny, means it is true. Today, that tomorrow, let us assume it is sunny, right? So this is a probability of sunny if play, how many times play was there, right? And probability of S by probability of sunny. So this is the base theorem, right? So what is the likelihood of this sunny out of so probability of what is this sunny if S is true, play was there. So how many days sunny days are there, and out of total possible means a possible play was there. So play was there out of 14, there is 10 times. 10 times play was there, right? 10 times play was there. Out of that, 3 days sunny, right? Sorry, 3 days sunny. So that is 0.3, and probability of sunny is out of 14 days. There is out of 14 days, 5 days sunny. So the likelihood value is 0.35, right? The probability of sunny is 0.35. And the probability of S out of 14, 10 days it is there. So 10 by 14, it is 0.71, right? So the probability of play possible the day is sunny is 0.3 into, that is 0.3 into 0.71 divided by 0.35. So the probability possible for play possible with the 60% probability if the day was sunny. No. We also need to check. Whether means play was not. What is the probability of not possible? No possibility of play, right? So probability of no if day was sunny. This is true. Sunny is true, means the day is sunny. So how many means what is the probability of no play, right? So for that, so among all the sunny days, how many times play was not there? Sorry. This is means out of no play days, how many days was sunny, right? No play is true, right? And how many times sunny was there, right? So this is, you can see no play was there. No play was there for four times, right? 4 times. Among that, 2 days was sunny. 2 days was sunny, right? So there are 4 no play days among those 14 records. So among those 4 days, 2 days was sunny. Right? So that is this no is true and sunny is how many days are sunny, right? So 2 by 4, that is 0.5, and probability of no is 0.29, and probability of sunny is 5 by 14, right? 0.35. So the probability of no play is 0.41, right? So you can see probability of S is greater than probability of no. So probability of this will win, right? So as we can see from the above calculation, that probability of S is greater than probability of no when the day was, when the day will sunny, right? So hence on sunny day, player can play the game, right? So here this is two binary classification, right? So if this is greater than some threshold, or this is greater than this one, so that's why you can see that the play was possible, right? Any questions, please? I'll take 2 minutes break, and if you have any questions, please type in the chat box. I'll take 2 minutes break.